The fabric of time. Let's start with one of the most fundamental questions humanity has ever asked. What is time? We take time for granted because it is so deeply embedded in the fabric of our daily experience. We see it in the way the Earth rotates on its axis, giving us day and night, and in the way it orbits the sun, giving us seasons and years. But when scientists look deeper, time turns out to be much stranger than we might think. In classical mechanics, time was absolute. Sir Isaac Newton viewed time as a constant, a river that flows at a steady pace. It was the same for everyone and everything. Time was like the background of the universe, something in which events took place, but itself was unchanging. But at the beginning of the 20th, at the turn of the century, this idea was turned on its head. In the year 1905, Albert Einstein published his special theory of relativity, and with it came one of the most fascinating concepts in physics. Time is relative. According to Einstein, the faster you move through space, the slower you move through time. Imagine two identical twins. One stays on Earth while the other travels in a spaceship traveling close to the speed of light. When the space-traveling twin returns, it will have aged significantly less than the twin that remained on Earth. This is not just a thought experiment. The phenomenon of time dilation has been confirmed by experiments with particles called muons and even with GPS satellites. But even more amazing is how Einstein linked space and time. He proposed that space and time are actually part of a single entity called space-time. Instead of viewing time as something separate from space, Einstein showed that they are interconnected, and that the fabric of space-time can be bent, stretched, and deformed by massive objects such as stars and black holes. This deformation of space-time is what we feel as gravity. So time is not absolute. It can stretch, shrink, and even stop under certain conditions, depending on your perspective and speed. But what does this mean for our understanding of time? How does this strange, malleable dimension govern the universe around us? The philosophy of time. What does time mean? On our journey, we looked at time from scientific, quantum mechanical, and even biological perspectives. But to truly understand the nature of time, we must also look at it from a philosophical perspective. In many ways, time is more than a dimension that can be measured by clocks or observed through the movement of the cosmos. It is a fundamental element of human existence. Philosophers have long asked the essential question: what does time mean to us, to the way we live, and to our understanding of reality? One of the most fascinating aspects of time is its relationship to existence. Time governs our lives from the moment we are born to the day we die and shapes everything we do. We experience life in a sequence of moments, past, present, and future. But we often wonder whether this is the true nature of time, or whether this is simply our perception of it. Let's take a look at one of the central debates in the philosophy of time: the contrast between presentism and eternalism. These two views offer opposing interpretations of how time works in relation to existence. Presentism states that only the present moment is real. In this view, the past has already disappeared, and the future has not yet appeared. We experience time as an unfolding sequence of moments in which each moment of the present is all that exists. For presentists, the idea of a block universe in which all moments exist simultaneously is absurd because it contradicts our basic life experience. From this perspective, time is always in the making, a series of moments that flow like a river from one to the next. Eternalism, on the other hand, proposes that all moments, past, present, and future, are equally real and exist together in a four-dimensional block universe. This idea is strongly supported by Einstein's theory of relativity, which, as we have seen, states that time is linked to space and can be stretched and bent depending on the observer. For eternalists, time does not flow as we perceive it. Instead, we simply move through a given structure of space-time. The past still exists, the future is already here, and the present is only a part of a much larger reality. This debate forces us to ask a crucial question. Is time something that happens to us, or is it something we experience as part of a larger structure of reality? If presentism is correct, we live in an ever-changing universe where time is a force that moves everything forward. But if eternalism is true, our experience of the flow of time could be an illusion, and the entire universe, including every moment of our lives, exists at once, with time just a way to order our experiences. Another fascinating aspect of time is the question of human consciousness. As we discussed in previous chapters, our brain constructs a sense of time based on processing sensory information, memories, and expectations about the future. But philosophers like Immanuel Kant have argued that time may not be an inherent property of the external world at all. Instead, Kant proposed that time is a fundamental feature of the way the human mind organizes experiences. According to this view, time is a mental construction, something our minds impose on the world in order to understand change and causality. This idea is further complicated by the fact that our perception of time can change dramatically under different circumstances. When we are bored or anxious, time seems to slip, while in moments of excitement or joy, time seems to fly by. The psychological experience of time is highly subjective and is influenced by our emotions, mental state, and attention. This suggests that time, at least as we experience it, may not be as objective as we think. The connection between time and memory is also crucial to our understanding of the present moment. Without memory, we would have no sense of the past, and without imagination, we could not anticipate the future. This has led some philosophers to argue that time does not exist in a vacuum, but is a byproduct of our brain's ability to remember the past and project into the future. In this view, the flow of time is intimately linked to the functioning of our consciousness, with each moment of consciousness weaving together memories and expectations to create a coherent sense of now. Are we free in a timeless universe? One of the deepest philosophical challenges associated with time is the question of free will. If the model of eternalism is correct and all moments, past, present, and future, exist simultaneously, do we really have the ability to make free decisions? Or is everything that happens to us, including our decisions, already fixed in this block universe? This has profound implications for our understanding of agency and responsibility. In the eternalist view, every decision we make is already part of the structure of time. You simply experience events that are predetermined and take place in a pre-existing timeline. This challenges the traditional notion of free will, which is based on the fact that we can change the future through our actions. If the future is already written, what does it mean to say that we control our destiny? In contrast, presentism offers more space for real freedom. If only the present is real, then the future is indeterminate, and our decisions in the present moment have the power to influence what happens next. In this model, time is open and fluid, and we have the opportunity to shape what happens in our lives through our actions and decisions. Presentism is closer to the way most people experience life, as a series of moments in which decisions matter and the future is not yet determined. But there is another twist to this debate: determinism. Even if presentism is correct and the future is open, some philosophers and scientists argue that the laws of physics could still determine everything that happens. According to causal determinism, every event in the universe is the result of a chain of cause-effect relationships dating back to the Big Bang. In this view, even if the future has not yet occurred, it is already determined by the physical laws that govern the universe. This means that although we feel as if we are making free choices, those choices are merely the inevitable result of previous conditions and events. At the heart of the human experience of time is our relationship with mortality. Time gives structure to our lives, but it also sets limits. We are painfully aware that our time on Earth is limited, and this awareness shapes how we live, how we make decisions, and how we search for meaning in life. Philosopher Martin Heidegger famously described humans as being toward death, and suggested that our mortality is not something we only encounter at the end of life, but is a fundamental part of our existence that shapes our experience of time from moment to moment. The fact that we are temporal beings raises profound questions about the meaning of life. If time is finite, how do we find purpose and meaning in the short amount of time we are given? For many, awareness of death gives life urgency and focus. The transience of time forces us to make decisions, invest in relationships, and seek fulfillment. The limitations of time make every moment precious. But what if time were infinite? If we lived forever, whether through biological immortality, digital consciousness, or some other means, would life still have meaning? Some philosophers argue that immortality could actually rob life of meaning. Without the pressure of time passing, we could lose our sense of urgency, and life could become monotonous and directionless. In this view, the finiteness of time is not a curse, but a blessing that gives structure and meaning to our existence. The philosophical study of time also intersects with metaphysics and the search for ultimate reality. Many philosophers, particularly in the Eastern traditions, have argued that time is an illusion, a veil that obscures a deeper, timeless reality. In Buddhism, for example, time is seen as part of the cycle of birth, death, and rebirth, samsara, that must be overcome in order to attain enlightenment and achieve nirvana, a state beyond time and change. Similarly, Hinduism teaches that the material world, with its changing forms and passage of time, is an illusion, Maya, and that ultimate reality is timeless and eternal, Brahman. In the Western tradition, philosophers such as Plotinus and Spinoza have also suggested that time is a feature of the finite world, but that ultimate reality exists outside of time. For these thinkers, time is part of the temporal order of the universe, but God or the infinite exists outside of time in a state of eternal presence. This idea is consistent with modern theories in physics that suggest that time may not be a fundamental property of reality, but rather an emergent feature of deeper, timeless laws of the universe. Ultimately, the philosophy of time challenges us to rethink not only our understanding of the universe, but also our understanding of ourselves. Time shapes every aspect of our lives, from the way we experience the world to the decisions we make and the meaning we find in life. But time is also one of the greatest mysteries, something we experience intimately but understand only imperfectly, or a construction of consciousness. Whether we live in a presentist or eternalist reality, and whether we can ever escape time or are forever bound to it, remains an open question. But as long as we are conscious beings traveling through time, the mysteries of time will continue to shape our thoughts, our lives, and our understanding of the cosmos. Time and the nature of the universe. Now that we've introduced the idea of time as a dimension intertwined with space, let's examine how this concept plays out on the largest scales imaginable, the universe itself. In 1915, Einstein expanded his ideas of special relativity to develop general relativity, which revolutionized our understanding of both gravity and time. One of the most important findings of general relativity is that massive objects bend space and time around themselves, which we experience as gravity. But what is crucial is that this curvature also influences time itself. The stronger the gravitational field, the slower time passes. You may be wondering how this plays out in everyday life. Even if we don't notice the time dilation caused by gravity in our daily lives, this effect is very real. For example, time passes a little slower on the Earth's surface than in space. The difference is tiny, but measurable. GPS satellites orbiting the Earth experience a weaker gravitational field than we do on the ground, which is why their onboard clocks tick slightly faster. Without correcting this time dilation, the GPS system would become inaccurate within a few hours. As we leave Earth, time's relationship to gravity becomes even clearer. Consider a black hole, a region of space where gravity is so strong that not even light can escape it. The closer you get to a black hole, the slower time passes relative to an observer who is far away. If you were to fall toward a black hole, an observer from a safe distance would see you slow down and take longer and longer to get closer to the black hole. In his view, you would never quite reach the event horizon, the limit beyond which nothing can return. But from your own perspective, time would continue as normal, and you would cross the event horizon in an instant, although you would never be able to report what happened after that. This leads us to a deep question. Does time have an end? In 1970, British physicist Stephen Hawking and Roger Penrose showed that the mathematics of black holes, when reversed, pointed to a singularity at the beginning of the universe, a moment in time when the density of the universe was infinite and time itself had a beginning. This is what we now call the Big Bang. But just as the Big Bang suggests a beginning of time, black holes offer the possibility that time, at least locally, can have an end. Inside a black hole, space and time swap roles. Once you cross the event horizon, moving forward in time is like being drawn into the singularity at the center of the black hole, where the curvature of space-time becomes infinite. This suggests that time can stop or collapse in some way inside a black hole. On the largest scale, the future of time in the universe remains an open question. The universe has been expanding since the Big Bang, but will it continue to expand forever, or will it eventually slow down, stop, or even reverse? The answer depends on the amount of mass and energy in the universe. If there is enough matter, gravity could eventually stop expansion and collapse the universe in a big crunch, potentially spelling the end of time itself. Alternatively, the universe could continue to expand indefinitely, eventually reaching a state in which stars go out, black holes evaporate, and time expands in an eternal, cold heat death. The implications of this are enormous. In one possible future, time could go on forever, but in another, time itself could eventually disappear into nothingness. These ideas push the boundaries of human imagination and challenge our fundamental understanding of reality. The arrow of time. Why does time only flow forward? On our journey into the mysteries of time, we encounter one of the most puzzling questions in physics. Why does time only seem to flow in one direction? In our everyday experience, time moves forward, from the past to the present to the future. This movement is called the arrow of time. But here's the strange thing. The fundamental laws of physics don't care about the direction of time. For example, if you watch a video of two billiard balls colliding with each other, you wouldn't be able to tell whether the video is playing forward or backward, because the laws of motion are symmetric in time. So why does it seem to us as if time only flows in one direction? The answer lies in a concept known as entropy. The second law of thermodynamics states that in a closed system, entropy increases over time. Entropy is a measure of disorder or randomness in a system. Imagine you have a brand new deck of cards, beautifully organized. If you shuffle the deck, it gets messier. The more you shuffle, the harder it becomes to return the deck to its original state. This increase in disorder is what we mean by increasing entropy. In the universe, time appears to flow toward increasing entropy. The reason we are experiencing a forward arrow of time is because the universe began in a state of incredibly low entropy, a highly ordered, dense state known as the Big Bang. From this point on, entropy has increased, driving the progress of time. Stars burn, galaxies form, and systems evolve, but always in ways that result in greater disorder. To illustrate this, imagine breaking an egg. Once the egg is cracked and scrambled, there is no easy way to return it to its original, unbroken state. This is the nature of the arrow of time. It is far easier to move from order to disorder than the other way around. But here's where it gets really fascinating. Although the arrow of time is a property of the macroscopic world, the microscopic world, the world of quantum mechanics, doesn't necessarily follow this rule. In the area of subatomic particles, processes can be reversible. An electron, for example, does not care whether it is moved forward or backward in time. This creates a paradox when we try to reconcile the temporally symmetrical world of quantum physics with the temporally asymmetrical world we experience. This paradox becomes particularly intriguing when we consider the heat death of the universe, a possible future scenario in which entropy reaches its maximum value. In this state, all energy would be evenly distributed, and there would be no more usable energy to do work, no shining stars, no life, no movement, just a cold, dark balance. When the universe reaches this state, will time continue to flow, or will it simply cease to have any meaning? There are other fascinating theories about the arrow of time. One idea is the concept of cosmic inflation, which states that the arrow of time is linked to the rapid expansion of the universe after the Big Bang. As space itself expanded at an extraordinary rate, this may have anchored the direction of the flow of time. Another theory involves quantum gravity and the role black holes could play in resetting time, perhaps in a cyclic universe where time exhibits different behavior in each cycle. Physicists have also wondered whether the arrow of time could be reversed under certain extreme conditions. For example, if the universe were to contract in a big crunch, could the flow of time also be reversed? Although this remains speculative, it raises profound questions about whether time as we know it is intrinsically linked to the expansion and cooling of the universe. Ultimately, the arrow of time appears to be closely linked to the evolution of the cosmos, entropy, and the forces that shape the universe. But as with many cosmic mysteries, we are left with more questions than answers. Time travel, fact, fiction, and the science behind it. The idea of time travel has fascinated the human imagination for centuries. From H.G. Wells' novel The Time Machine to films like Back to the Future, we dream of going back in time to experience historical events or looking into the future to see what awaits us. But could time travel actually be possible? Let's explore what modern science says about this tantalizing prospect. First, we want to clarify the question: what does physics allow? Although time travel may sound purely science fiction, the equations of physics, particularly Einstein's theories of relativity, do not completely rule it out. In fact, they offer a few possible paths. One of the most promising avenues for time travel comes from special relativity, which shows that the faster you move, the slower time passes. The closer you get to the speed of light, the more extreme the time dilation becomes. This is known as the twin paradox, a thought experiment in which one twin travels through space near the speed of light, while the other remains on Earth. When the space traveler returns, he will have aged much less than his sibling, a form of time travel into the future. This type of time dilation is not just theoretical. It has been observed in particle accelerators, in which particles move close to the speed of light and experience time much more slowly. In fact, the lifespan of so-called muons, which normally have a very short lifespan, is significantly extended when they travel at high speeds. Essentially, these particles experience a kind of time travel into their future. But what about time travel to the past? This is where things get more complicated. General relativity offers some tantalizing possibilities. One involves wormholes, theoretical tunnels through space-time that could connect distant points in space and time. These shortcuts through the universe are solutions to Einstein's equations, first proposed by physicists Albert Einstein and Nathan Rosen in 1935, which is why wormholes are sometimes called Einstein-Rosen bridges. A wormhole could theoretically enable not only travel over large distances in space, but also travel into the past or future. Imagine 2 points on a piece of paper that represent different moments in time. If you bend the paper, you could bring these 2 points together, so you could jump back and forth between them instantly. That's the basic idea of a wormhole. It folds space-time. However, there are enormous challenges in making this a reality. First, if wormholes exist, they would likely be extremely unstable. They could collapse as soon as something tries to pass through them. Second, traveling through a wormhole could involve intense gravitational forces that would tear apart anything that attempted to make the journey. And third, we have no experimental evidence that wormholes actually exist. They remain purely theoretical constructs. Another possible method for traveling back in time comes from the concept of closed time-like curves, CTCs. These are solutions to Einstein's equations, which allow paths in space-time that lead back to themselves. Imagine driving in a straight line, but ending up back where you started. This is exactly what a CTC would enable, but in the dimension of time. Some physicists, like Kurt Gödel, suggested that rotating universes could allow such time loops. But even if time travel is theoretically possible, it raises a number of paradoxes. The best known is the grandfather paradox. Imagine traveling back in time and accidentally preventing your grandfather from meeting your grandmother. If they never meet, your parent is not born, which means you are not born. So how could you have traveled back in time? This logical contradiction poses a significant problem for time travel into the past. Physicists have proposed solutions to this problem. One possibility is the idea of multiple timelines, or parallel universes. In this scenario, traveling back in time would create a new, alternate timeline in which the events of the past unfolded differently. This means you could change events without affecting the timeline you came from. This is a concept often explored in science fiction, but it has some basis in quantum mechanics, particularly the many worlds interpretation, which states that every quantum event results in a bifurcation of realities. Theoretical physicist Igor Novikov proposed another way to solve time travel paradoxes. the self-consistency principle. This idea states that if time travel is possible, then the events of the past are fixed and unchangeable. In other words, every action a time traveler takes in the past must already be part of history, thus avoiding paradoxes. If you tried to stop your grandparents' marriage, some event would intervene to stop you because the timeline is self-consistent. Another fascinating aspect comes from quantum mechanics. In 1991, physicist David Deutsch suggested that quantum mechanics could allow a version of time travel that avoided paradoxes. In his model, a time traveler would essentially create a new quantum branch in which the future unfolds differently without changing the past of the original timeline. While this doesn't solve the practical problems of time travel, it shows that the fundamental rules of quantum physics could make time travel possible under certain conditions. Despite all the considerations, the biggest obstacle remains technology. Approaching the speed of light or creating a stable wormhole requires energy levels far beyond what humanity can currently generate. To achieve the speeds required for significant time dilation, we would need propulsion systems that far exceed our current capabilities. And wormholes, if they exist, could require exotic matter with negative energy to stay open, something we haven't discovered or created yet. For now, time travel remains a tantalizing possibility, trapped in the realm of theory. But the science behind it continues to inspire new ideas and a deeper understanding of how time, space, and the universe are connected. Time in quantum mechanics. Does time even exist at the quantum level? As we delve deeper into the nature of time, we must confront the world of quantum mechanics, the branch of physics that studies the behavior of the smallest particles in the universe, such as electrons, photons, and quarks. The quantum world is notoriously strange, with particles behaving in ways that challenge our everyday understanding of reality. And when we examine time at the quantum level, things get even stranger. In the classic everyday world, time appears to flow smoothly, as if events are moving continuously from the past to the present to the future. But at the quantum level, this orderly flow of time begins to unravel. Quantum mechanics describes a universe in which particles exist in multiple states simultaneously, a phenomenon known as superposition, and can be instantly connected to one another over large distances, an effect called quantum entanglement. But how does time fit into this bizarre landscape? To answer this question, we need to delve into the Schrödinger equation, the foundation of quantum mechanics. This equation describes how quantum systems evolve over time. But there's something strange about it. In the Schrödinger equation, time doesn't flow in a specific direction. Just like the laws of classical physics, it treats the past and the future as equal, meaning that at the quantum level, there is no inherent reason why time should only move forward. This symmetry of time in the quantum realm raises a profound question. Why do we even experience time as something that only flows in one direction? One possible explanation comes from the process of quantum measurement. When a quantum system is observed, its superposition, the ability to exist in multiple states at once, collapses into a single state. Before the measurement, the particle could be in several places at the same time or have several values. After the measurement, it selects a result. This act of measurement seems to capture a moment in time and gives us the impression that time flows from the past into the future. But does this collapse imply that time itself is created or shaped by observation? Some physicists suggest that our perception of the arrow of time may arise from the way we interact with quantum systems. From this perspective, time could be an emergent property of a deeper, timeless quantum reality. Another fascinating phenomenon in the quantum world that challenges our understanding of time is entanglement. When two particles are entangled, their states become linked, no matter how far apart they are. When you measure the state of one particle, you immediately know the state of the other, even if it is at the other end of the universe. This instant connection seems to contradict the usual rules of cause and effect, where information can only be transmitted at or below the speed of light. But here, time becomes even more mysterious. The entanglement seems to function outside of time. It is as if time does not affect the connection between entangled particles. This idea leads to an intriguing question. Could time itself be an illusion in the quantum world? Some physicists believe that at the deepest level of reality, time may not exist at all. This idea is explored in theories of quantum gravity, in which space and time are viewed as emergent properties rather than fundamental building blocks of the universe. One of the leading candidates for a theory of quantum gravity is loop quantum gravity. In this framework, space-time is not continuous, but rather consists of tiny, discrete loops, much like the pixels on a digital screen. If this is true, time, like space, could be quantized at the smallest level. In other words, there would be no smooth flow of time, but rather tiny, indivisible units of time. Between these entities, time would not exist at all, and our experience of a continuous passage of time could be an illusion created by the way we perceive these quantum ticks. Another important theory of quantum gravity is string theory, which also proposes that time and space are not fundamental, but arise from simpler structures. In string theory, particles are not point-like objects, but tiny vibrating strings, and the dimensions of time and space could arise from the interaction of these strings. According to this view, time as we know it may be a secondary effect of a deeper, more complex reality. One of the most radical ideas in quantum mechanics comes from the Wheeler-DeWitt equation, which attempts to connect general relativity with quantum mechanics. Remarkably, time does not exist in this equation at all. The equation describes a universe in which everything exists in a timeless state. This has led some physicists to suggest that time is not a fundamental aspect of reality, but rather something that only arises under certain conditions, similar to how temperature arises from the collective behavior of molecules. This radical concept of a timeless universe challenges everything we think we know. When time is not fundamental, it forces us to reconsider the nature of existence itself. In a timeless universe, the past, present, and future could exist simultaneously, and what we experience as the flow of time could be nothing more than a perception shaped by our own consciousness. To make things even more complex, quantum mechanics introduces the concept of quantum tunneling, in which particles can tunnel through barriers that they are not supposed to overcome according to classical physics. In some interpretations, this tunneling occurs in a way that suggests particles traverse time in a non-standard way, adding another layer of mystery to the quantum nature of time. As we have seen, time in the quantum world behaves in ways that contradict our everyday intuition. At the smallest level, time could be an illusion, a consequence of deeper, more fundamental processes. Yet despite the strangeness of the quantum realm, our experience of the arrow of time, the movement from the past to the future, remains. How these two aspects of time fit together is one of the greatest mysteries of modern physics. The nature of time and black holes, when time stands still. If we delve deeper into the mysteries of time, we come across one of the most extreme environments in the universe, black holes. These cosmic objects are so massive and dense that they warp space-time to such an extent that even light cannot escape their gravitational field. Black holes push our understanding of physics and time to its limits. Einstein's general theory of relativity states that massive objects bend space-time, and the more massive an object is, the more space-time around it is curved. A black hole represents the extreme end of this concept. At the center of a black hole lies a singularity, a point at which the curvature of space-time becomes infinite and our current understanding of physics fails. This is where time as we know it could cease to exist. To understand how time behaves near a black hole, let's first consider what happens when an object approaches it. Let's imagine an astronaut falling towards a black hole. The closer he gets, the stranger what happens. Time begins to pass more slowly for him, at least from the perspective of an observer who is at a safe distance. The closer the astronaut gets to the black hole's event horizon, the point of no return, the slower his clock appears to be ticking to the distant observer. In fact, from the observer's perspective, time appears to stop for the astronaut as soon as he reaches the event horizon. The astronaut, on the other hand, would continue to experience time normally, but would be unable to communicate this because he is trapped in the black hole's gravitational field. This is an example of so-called gravitational time dilation, a phenomenon predicted by general relativity. The stronger the gravitational field, the slower time passes. This effect becomes extreme near a black hole. If you observe the astronaut from a safe distance, you would see him freeze at the event horizon. From his own perspective, however, he would fall over the horizon and continue toward the singularity, oblivious to the time dilation. The event horizon is fascinating in itself. It is the limit beyond which nothing can escape the black hole's gravitational field, not even light. But it also marks the limit at which our understanding of time undergoes a radical transformation. For an object that falls into a black hole, time only flows in one direction, towards the singularity. The singularity at the center of the black hole is a point of infinite curvature where space-time is stretched infinitely. Within the event horizon, space and time essentially swap roles. For the object falling into the black hole, the advance of time means that it is inexorably approaching the singularity, and there is no way back. Physicists are still wrestling with the question of what is happening at the singularity itself. General relativity predicts that all matter inside the black hole is compressed to an infinite density, and space-time reaches infinite curvature. This means that all known laws of nature collapse at the singularity, including our understanding of time. Time could end at the singularity. The concept of time as we experience it may simply no longer apply there. This represents one of the greatest challenges in modern physics, unifying general relativity, which describes large structures, with quantum mechanics, which describes tiny particles, to develop a complete theory of quantum gravity. But the story of time and black holes does not end there. Theoretical physicist Stephen Hawking revolutionized our understanding of black holes in the 1970s with his discovery of so-called Hawking radiation. Hawking showed that black holes are not completely black. They can emit radiation near the event horizon due to quantum mechanical effects. Over time, a black hole loses mass due to this radiation and can eventually evaporate. This raises an intriguing question. What happens to the information about the matter that fell into the black hole? When the black hole finally disappears, what happens to all the information it held? This leads to the black hole information paradox, one of the hottest debates in theoretical physics. According to quantum mechanics, information about a physical system must be preserved. But when a black hole evaporates and disappears, where does the information about everything it absorbed go? Hawking initially suggested that the information was lost, but this idea contradicted quantum mechanics. Recent research suggests that the information could somehow escape from the black holes, perhaps encoded in Hawking radiation. But a final resolution to this paradox has yet to be found. Now let's look at what happens when two black holes collide. In the year 2016, scientists made a groundbreaking discovery with the first detection of gravitational waves, ripples in space-time created by massive objects such as colliding black holes. These waves were predicted by Einstein a century earlier, but had never been observed until the LIGO experiment, when the collision of two black holes was discovered more than 1 billion light-years away. This event opened a new window on the universe, allowing us to observe cosmic phenomena not through light, but through the fabric of space-time itself. Gravitational waves also offer new insights into the nature of time. The waves they create propagate through space-time at the speed of light, but they also slightly distort the passage of time as they pass through. As a gravitational wave passes, it stretches and compresses space-time, subtly altering the flow of time. In this way, black holes don't just affect time locally near their event horizons. They send temporal distortions as waves through the universe. But can we ever use black holes to manipulate time? Some physicists have speculated about using black holes as potential gateways for time travel. Theoretical physicist Kip Thorne famously explored the idea of using a rotating black hole, also called a Kerr hole, as a type of time machine. In theory, a rotating black hole could create a closed time-like curve, a loop in space-time that would potentially allow travel back in time. However, such a journey would likely involve significant dangers, including intense gravitational forces, cosmic radiation, and of course the challenge of surviving the singularity. Ultimately, black holes provide some of the most extreme examples of how time can behave in ways that contradict our everyday experience. From gravitational time dilation to the evaporation of black holes through quantum mechanical processes, they challenge our understanding of time at every level. As we continue to explore black holes, we may not only learn more about the universe's most mysterious objects, but also reveal deeper truths about the nature of time itself. Time and the multiverse. Infinite time, infinite realities. As we continue our exploration of the nature of time, we encounter one of the most exciting and fascinating concepts in modern cosmology, the multiverse. The idea of the multiverse suggests that our universe could be just one of many, each with its own version of space, time, and physical laws. This opens up the possibility that there is not just one timeline, but an infinite number of timelines, each with its own unique version of reality. The concept of the multiverse comes from various branches of physics, but one of the most compelling arguments comes from cosmic inflation. In a fraction of a second after the Big Bang, the universe is thought to have undergone a period of rapid expansion known as inflation, which stretched space faster than light. However, this inflation process did not occur uniformly throughout the cosmos. Instead, some regions of space continued inflation, while others slowed, eventually forming pockets of space-time, each of which could become its own universe. This idea is called perpetual inflation. According to the theory of eternal inflation, the rapid expansion of space-time could continue indefinitely, with new universes bifurcating water from the expanding space-time like bubbles in a boiling pot. Each of these bubble universes could have different properties, different physical constants, and different laws of nature. If this theory is correct, our universe is just a bubble in a vast multiverse. But how does time work in a multiverse scenario? If there are infinite universes, does that mean there are also infinite timelines? And what does this mean for our understanding of the flow of time? One possibility is that each universe in the multiverse has its own version of time, with its own beginning and end. In some universes, time could flow linearly from the past to the future, like in our universe. In others, time might be cyclical, repeating itself in an endless cycle. Still in others, time might flow in ways we can hardly imagine. Perhaps time flows sideways or even backwards. This brings us to the concept of parallel universes, which is often associated with the multiverse theory. In quantum mechanics, the many worlds interpretation proposes that each time a quantum event occurs, such as a particle in a superposition state, the universe is split into multiple branches, each representing a different outcome. This means that every decision we make, every roll of the dice, every moment of chance creates a new universe in which different possibilities unfold. If the many worlds interpretation is correct, there could be an infinite number of versions of you, each with a different passage of time in a parallel universe. This raises profound questions about the nature of time in these parallel universes. If each universe has its own timeline, does that mean that time itself splits into an infinite tree of possibilities? Could it be that in one universe you're reading this script while in another you're doing something completely different? The concept of time becomes more fluid and expansive when viewed through the prism of the multiverse. Another fascinating implication of the multiverse is the possibility of time loops. If the multiverse is infinite and time continues forever in some universes, it is possible for certain events to repeat themselves, leading to time cycles in which the same events happen over and over again. This is similar to the idea of eternal recurrence, a concept in philosophy that proposes that the universe and all of its events could repeat themselves in an endless cycle. In a multiverse with an infinite number of timelines, eternal recurrence could take place on a cosmic level. One of the most profound ideas in multiverse theory is that the Big Bang, the beginning of time as we know it, was not a unique event. In some versions of the multiverse theory, our universe could have arisen from the collapse of a previous universe, or it could be one in a series of infinitely many universes created and destroyed in an endless cycle. This idea is studied in cyclic models of the universe, in which the Big Bang is just one phase in a continuous process of expansion and contraction. In such a model, time itself could be infinite, with no real beginning or end. The idea of multiple universes is also linked to the anthropic principle, which proposes that the reason we observe a universe so perfectly suited to life is because we happen to be in one of the few universes where the conditions are just right for life to exist. In this view, there could be countless other universes in which time, space, and matter function in ways that make life impossible. We are in this universe because it is one of the rare universes in which time flows in such a way that complex structures such as stars, planets, and living things can emerge. But can we ever observe or interact with these other universes? The answer remains unclear. Some physicists speculate that certain types of quantum fluctuations or gravitational effects could allow us to detect the presence of other universes, but so far there is no direct evidence of the multiverse. However, some theories in string theory and quantum mechanics suggest that the laws of nature could indicate the existence of other universes, even if we cannot directly observe them. One of the more speculative ideas is that black holes could serve as gateways to other universes. According to some interpretations of quantum gravity, matter falling into a black hole could be funneled into a new universe, where it would form the seed of a new Big Bang. If this is true, each black hole in our universe could represent the birth of a new universe, each with its own version of space, time, and physical laws. This idea remains highly theoretical, but shows how closely the concepts of time, space, and the multiverse could be connected. Finally, we should consider the role of consciousness in the multiverse. Some physicists, such as Nobel laureate Roger Penrose, have suggested that consciousness itself may be linked to the quantum nature of reality. If the many worlds interpretation is correct, every decision we make could create a new reality, and our consciousness could play a role in navigating these infinite timelines. In this view, consciousness may be connected to the flow of time in ways that we do not yet fully understand. So what does the multiverse mean for our understanding of time? If infinite universes exist, time itself could be just one of many possible ways of experiencing reality. The multiverse suggests that there could be infinite versions of time, each tied to a different universe and with its own rules and possibilities. Whether we will ever be able to enter or observe these other timelines remains unclear, but the idea of the multiverse forces us to view time not as a single thread, but as a vast, branching web of possibilities that stretches across the entire universe. Time and the beginning of the universe. What happened before the Big Bang? The Big Bang theory is the dominant explanation for the origin of the universe. It describes a moment about 13.8 billion years ago when the universe exploded from an incredibly hot, dense state into the vast, expanding cosmos we observe today. This is the point at which time, as we understand it, begins. But this theory raises a crucial question. What happened before the Big Bang? The short answer, according to many physicists, is that the question, what happened before the Big Bang, may not make sense. In Einstein's general theory of relativity, time itself is tied to the fabric of the universe. If space and time are intertwined, as general relativity suggests, then there was no before of the Big Bang because time did not yet exist. In this view, time, like space, emerged at the moment of the Big Bang. But this answer, as much as it agrees with the theory of relativity, leaves many dissatisfied. Could there be more to this story? One possible explanation comes from quantum cosmology, which attempts to combine general relativity with quantum mechanics, the physics of the very small. Quantum mechanics has the strange property of indeterminacy, where particles can exist in multiple states at the same time and only transition to a particular state when they are observed or measured. Some cosmologists have suggested that before the Big Bang, the universe existed in a kind of quantum mechanical superposition in which time itself was fuzzy and indeterminate. One influential idea came from physicist Stephen Hawking, who in the 1980s developed a theory known as the no-boundary condition. Hawking proposed that the universe does not have a sharp beginning, but instead has a smooth, curved geometry that makes the question of before irrelevant. In his model, time near the Big Bang behaves like a dimension of space, meaning that the further back you go to the origin of the universe, the distinction between time and space becomes blurred. If we could travel back to the Big Bang, time itself would gradually disappear and only space would remain. According to this view, there was no moment at which time began. It simply transformed from a spatial dimension into the fluid time we experience today. This idea is closely related to the concept of imaginary time, a term from theoretical physics in which time behaves mathematically, like another spatial dimension. In this framework, the universe could have emerged from a timeless, spaceless state, with time as we know it only emerging as the universe expanded. Imaginary time smooths out the singularity, the infinite point at which general relativity collapses, and allows for a continuous transition from the before of the Big Bang to the after. Other theories suggest that our universe may be just one part of a much larger, timeless structure. One possibility is that the Big Bang was not the absolute beginning, but rather the result of a cyclical process in which the universe goes through phases of expansion and contraction. In these cyclical models, the universe could collapse in a big crunch, followed by a new Big Bang, with time resetting with each new cycle. This idea challenges the traditional view that the universe is heading toward a final heat death, the final cold state in which all energy is evenly distributed and nothing new happens. Instead, the end of one universe could mark the beginning of another. Physicist Roger Penrose proposed a variant of this idea with his theory of conformal cyclic cosmology. According to Penrose, the universe is expanding so much that eventually all the particles and structures in it are erased, leaving an empty vacuum. In this state, the geometry of the universe becomes scale-independent, meaning that time and space no longer have a defined scale. This allows a new Big Bang to arise from the remnants of the previous universe, effectively restarting time. One of the most radical ideas comes from string theory and the concept of brains, short for membranes. In string theory, our universe could just be a three-dimensional brain floating in a higher dimensional space. If this is true, the Big Bang could have been caused by a collision between our brain and another brain, releasing enormous amounts of energy and creating the universe as we know it. This scenario is called the ekpyrotic model and suggests that brain collisions could be responsible for multiple Big Bangs, each creating a new cosmos. String theory also gives rise to the concept of the multiverse, which we discussed in the previous chapter. In some versions of the multiverse theory, new universes are constantly emerging, each with its own version of time and space. In this view, the Big Bang that created our universe may have been just one of countless Big Bangs occurring throughout the multiverse. Each universe could have its own timeline, and the concept of the before of the Big Bang becomes meaningless, since other universes may have always existed parallel to ours. Another fascinating possibility comes from studying quantum gravity. One of the leading approaches to quantum gravity is loop quantum gravity, which proposes that space-time is made up of tiny, discrete loops rather than being continuous. In loop quantum gravity, the Big Bang may not have been the beginning of time, but rather a transition from an earlier phase of the universe. Some models predict a big bounce, in which the universe shrinks to a minimum size and then expands again, with time continuing continuously throughout the cycle. This would mean that there was a universe before the Big Bang, and time may extend infinitely into the past. Even more speculative ideas suggest that time itself may be a localized phenomenon, meaning that time as we know it may only exist in certain regions of the multiverse or within certain phases of the universe. Outside these regions, time may not exist or function in ways we do not yet understand. This idea challenges the idea that time is a universal constant and instead suggests that time could be just one of many possible experiences of reality. Despite these intriguing theories, the question of what happened before the Big Bang remains open. The limits of our current understanding of physics mean that we cannot directly observe or test what happened before the Big Bang, if anything happened at all. However, advances in fields such as quantum cosmology, string theory, and gravitational wave astronomy could one day provide new clues. Ultimately, the question of whether time has a definite beginning or whether it extends back infinitely into the past in some form remains one of the greatest mysteries in cosmology. The origin of time is deeply connected to the origin of the universe itself, and as we continue to explore the nature of reality, we may discover that time is much stranger and more fluid than we ever imagined. Time and the flow of time, is it an illusion? Having explored the fundamental ways in which time shapes our universe, we must now confront one of the most controversial and intellectually challenging ideas in modern physics. Is time itself an illusion? Could it be that our perception of time, the ticking of the clock, the succession of events, the progression from the past to the future, is not a fundamental feature of the universe, but a construction of human consciousness? This idea has deep roots in both physics and philosophy. In 1988, British philosopher J.M.E. McTaggart argued that time is an illusion in his famous essay, The Unreality of Time. He divided time into two ways of understanding it: the A series, in which events are ordered as past, present, and future, and the B series, in which events are ordered in terms of earlier and later, but without the notion of a progressing now. McTaggart believed that the A series, which gives us the feeling of a fluid present, is illogical because it relies on an ever-changing present moment. He concluded that time, at least as we experience it, must be unreal. Modern physics, particularly the theory of relativity, adds further fuel to this philosophical fire. According to Einstein, the passage of time is relative. Different observers may experience time differently depending on their speed and the strength of gravity. This leads to a concept known as a block universe, in which the past, present, and future coexist simultaneously. In the block universe model, time is like a spatial dimension. Every moment is equally real, and the flow of time is an illusion created by our limited perspective. To imagine this, imagine the universe as a loaf of bread. Each slice of the loaf represents a moment in time. The entire loaf exists at once, but you, as the observer, experience only one slice at a time, the present moment. The past slices still exist, and the future slices are already there, waiting to be experienced. From this perspective, time does not flow. Instead, we move through the slices of time, and the sense of progression is simply our brain's way of processing the world. This idea is supported by the equations of relativity, which treat time as a dimension like space. Just as all points in space exist simultaneously, all points in time also exist simultaneously. The difference between past, present, and future is, as Einstein himself said, a stubbornly persistent illusion. But this raises a profound question. If time is just another dimension like space, why do we experience it so differently? Why does time seem to flow from the past to the future, but not the other way around? The answer may lie in the concept of entropy, which we have already explored. The second law of thermodynamics states that entropy, or disorder, in a closed system tends to increase over time. It is this increase in entropy that creates the so-called arrow of time, the irreversible progression from the past into the future. However, some physicists argue that the increase in entropy is not a fundamental feature of the universe, but rather a statistical phenomenon that arises from the way we experience time. In this view, the universe may have started in an extremely low entropy, high-order state at the Big Bang, and entropy has increased since then, giving us the feeling that time is flowing forward. But this arrow of time is not an absolute law. It is just a consequence of the initial conditions of the universe. Should the universe contract or enter a new phase, the arrow of time could reverse, or time could behave in ways we do not yet understand. Quantum mechanics adds another layer of complexity to the question of the reality of time. In the quantum world, particles can exist in multiple states simultaneously, and events do not unfold in a simple linear sequence. The Schrödinger equation, which describes the behavior of quantum systems, does not distinguish between the past and the future. It treats time symmetrically, meaning that quantum processes could theoretically unfold in either direction. But when we measure or observe a quantum system, its state collapses into a clear result, giving us the feeling that time flows in one direction. Some physicists, such as Carlo Rovelli, have suggested that time may be an emergent phenomenon, not something fundamental. In Rovelli's view, time arises from the way we interact with the world on a macroscopic level. The deeper we delve into the quantum world, the less relevant the concept of time becomes. This leads to the idea that time is relational, that it exists only in relation to the things that happen in the universe, rather than being an absolute background framework through which events unfold. If nothing changes, time could have no meaning. In this sense, time could be an emergent phenomenon arising from the interactions of the particles and forces in the universe, rather than being something that exists independently. The idea that time is an illusion or an emergent phenomenon has profound implications for our understanding of reality. If time is not fundamental, the entire structure of causality, the idea that one event causes another, which causes the flow of time, could be a human construction rather than an objective truth. In a timeless universe, everything could already exist, and our experience of cause and effect could just be the way our brains process information. There are also interesting parallels between the illusion of time and consciousness. Some theories of consciousness suggest that our brain creates the sense of a fluid present by linking memories of the past and anticipations of the future. In this view, the passage of time is not something that exists out there in the universe, but rather something that is constructed in here in our minds. Neurologically, our brains seem to process time in a way that creates the illusion of continuity. Studies show, for example, that we experience the present moment in short intervals, so-called perceptual images, which our brain then smooths into a continuous experience. This suggests that what we perceive as a fluid flow of time may be more like a series of snapshots or still images, much like a film played frame by frame. The concept of timelessness is also explored in certain meditative and spiritual traditions. For thousands of years, mystics and philosophers have spoken of moments of deep contemplation in which time seems to disappear and only a pure sense of the present remains. Could these experiences reflect a deeper truth about the nature of time, that it is not fundamental, but rather something imposed by our everyday consciousness? Despite all this, time remains one of the deep-rooted features of our experience. Even if time is an illusion, it is a powerful one, shaping our memories, guiding our decisions, and providing the structure for the narratives of our lives. Ultimately, whether time is an illusion or not, we cannot escape its influence. The mysteries of time challenge not only our understanding of the universe, but also our sense of identity and existence. We live in time, but perhaps we will never fully understand what time really is. Whether time flows forward, exists as a static block, or arises from deeper principles we have not yet discovered, it remains one of the most enduring and profound mysteries of the cosmos. The future of time. Where are we going? As we conclude our journey through the mysteries of time, we ask ourselves, what does the future hold for our understanding of time? Time is not only a topic of scientific and philosophical debate, it is also at the heart of many of the challenges we face as humanity. Our ability to manipulate and understand time could shape the future of technology, space exploration, and even the survival of humanity. One of the most intriguing possibilities is whether we will ever be able to manipulate time on a large scale. As we have seen, time can be manipulated even on small scales, through phenomena such as time dilation. We've observed this in experiments with particles traveling close to the speed of light, and we've even taken it into account in the operation of GPS satellites, which have a slightly different perception of time due to the weaker gravitational field in orbit. But what about larger, more practical manipulations of time? Could we one day slow down or speed up time at will? Of course, time travel is the ultimate goal for those who want to manipulate time. While time travel into the past is fraught with paradoxes and seems unattainable with our current understanding, time travel into the future is not only possible, but has already been proven under very specific circumstances. The faster you travel, the slower time passes relative to those you leave behind. If we ever develop the technology to travel near the speed of light, for example with relativistic spacecraft, we could send explorers on journeys that cause them to age much more slowly than those who remain on Earth. A journey to a distant star could theoretically last only a few years from the traveler's perspective, whereas decades or even centuries pass on Earth. This opens up the possibility of deep space exploration, where astronauts could travel far beyond our solar system without experiencing the same passage of time as people on Earth. This type of time manipulation is called travel time dilation and could have profound effects on how we explore the universe. Imagine being able to travel to the far future simply by traveling at near the speed of light or even forward in time to see what becomes of humanity. In theory, time dilation could allow us to experience the distant future of the universe, billions or trillions of years from now. Another interesting area of research is the potential change in our perception of time. While the manipulation of time itself on a large scale remains a distant dream, our perception of time is far more malleable. Scientists are already studying how the brain processes time, and it's possible that future technologies could allow us to speed up or slow down our subjective experience of time. For example, neural implants or advanced virtual reality systems could one day make it possible to compress hours of experience into seconds or extend moments of pleasure, seemingly indefinitely. This could revolutionize the way we experience entertainment, learning, and even life itself. Beyond human experience, the study of artificial intelligence also raises fascinating questions about time. AI systems work at speeds far beyond human cognition, processing information and making decisions in fractions of a second. As AIs become more advanced, they could develop a concept of time that is completely alien to us, with milliseconds representing vast spans of subjective time to them. Could future AIs perceive centuries of human history as mere moments? And could they find new ways to understand and manipulate time that we cannot yet imagine? Then there is the question of time and the future of the universe. As we mentioned earlier, the universe has been expanding since the Big Bang, and this expansion is currently accelerating due to a mysterious force called dark energy. But what does that mean for time? If the universe continues to expand indefinitely, it could lead to a condition known as thermal death or the Big Freeze, in which all matter and energy is stretched so far apart that nothing can happen. In this scenario, time as we experience it could lose meaning because there would no longer be any events, no changes, no processes in progress. But there are other options. Some theories suggest that the universe could stop expanding and collapse again, causing a big crunch that would potentially trigger a new Big Bang and time cycle. In this model, time would be cyclical, with each universe experiencing its own birth, evolution, and death, only to be reborn. The future of time, in this sense, could be eternal, with endless cycles of creation and destruction. Another possibility is that the multiverse contains universes where time works differently. In some universes, time could flow backwards, or there could be no time at all. If the multiverse theory is correct, then time as we know it could be just one of many possible ways in which reality can unfold. The future of time could involve not only the continuation of our universe's timeline, but also the exploration of entirely new time forms in the multiverse. On a more practical level, understanding time could revolutionize technology in ways we cannot yet imagine. For example, quantum computing already exploits the strange properties of quantum mechanics in which particles exist in superpositions of states and can be entangled with one another over long distances. Quantum computers could theoretically perform calculations far faster than any classical computer by exploiting the timeless parallel nature of quantum states. Could future quantum technologies allow us to directly manipulate time at the quantum level? Time crystals are another field of research at the forefront of science. These strange states of matter, first theorized in 2012 and later observed in experiments, exhibit a form of perpetual motion at the atomic level. Time crystals do not repeat in space like normal crystals, but in time. Their atoms oscillate in a regular pattern, even in the lowest energy state. This discovery challenges our understanding of time and suggests that there may be hidden symmetries and structures in time itself that we have not yet fully explored. There is also the potential for breakthroughs in quantum gravity, the attempt to unify quantum mechanics and general relativity into a single theory. One of the greatest challenges in physics is understanding how time works at the quantum level, where the smooth flow of time breaks down and strange phenomena such as quantum entanglement and superposition dominate. If we can unlock the secrets of quantum gravity, we could gain a whole new understanding of what time really is, not just in the context of our universe, but in all possible universes. Finally, there is the profound philosophical and ethical question of immortality. As humans, we are bound by time. Our lives unfold in a series of moments, and death marks the end of our personal timeline. But what if time no longer limited us? Advances in biotechnology, genetic engineering, and nanotechnology could one day make it possible to extend human lifespans indefinitely, or even upload our consciousness into machines, effectively leaving us out of the biological time frame. If we stopped aging or dying, what would time mean to us? Would we continue to experience it as linear progress, or would immortality change our relationship to time in ways we cannot yet foresee? In the end, the future of time is as vast and mysterious as time itself. Whether we will one day travel through time, manipulate its flow, or overcome it entirely remains to be seen. But one thing is certain: our journey to understand time is far from over. As we continue to push the boundaries of science, philosophy, and technology, time will remain one of the greatest mysteries of the universe and one of the most exciting frontiers for human exploration. The nature of time and consciousness. How time shapes our perception of reality. To conclude our deep dive into the mysteries of time, we must address one final, profound question. What role does consciousness play in our experience of time? Is time something that exists independently of us, or is it closely linked to the way we perceive the world? The relationship between time and consciousness has preoccupied both philosophers and scientists for centuries, and recent developments in neuroscience, psychology, and physics are bringing us closer to answering the question of how these two fundamental aspects of our reality are connected. In the simplest sense, consciousness is the awareness of one's surroundings, thoughts, and feelings. But more than that, consciousness seems to require a sense of time. After all, how could we be aware of anything without an awareness of the present moment, memories of the past, or the ability to anticipate the future? Time provides the framework within which our conscious experience unfolds. But how does this happen? And is time something our brains construct, or does it exist outside of us, waiting to be perceived? Let's start with the question of how our brain processes time. For us, time is an ongoing, continuous flow from one moment to the next. Neuroscience shows that our perception of time is anything but simple. Our brains don't process time in a smooth, continuous way. Instead, they appear to break down time into chunks or images, which are then assembled into what we perceive as a continuous experience. Research suggests that we experience the present moment in intervals of about 3 seconds. This is called the apparent present, a window of time in which our brain gathers sensory information before piecing it together into a coherent experience. This process of breaking time into images allows our brains to create the illusion of a steady flow of time, but it is not perfect. Anyone who has experienced how time flies during an exciting activity or drags on during a boring task has felt how malleable our perception of time can be. This variability suggests that time as we experience it is not an objective property of the universe, but rather something shaped by our cognitive processes. This raises an important question. Is time itself a product of consciousness? In other words, does time exist only because we are aware of it, or does it exist independently of us and we are merely observers? This question is at the heart of the philosophical debate between presentism and eternalism. Presentism is the view that only the present moment exists. The past is past, and the future is yet to come. In this view, consciousness is crucial to time, because the present moment represents the only reality. Eternalism, on the other hand, suggests that the past, present, and future exist simultaneously in a block universe, and consciousness is just a tool for traversing this static reality. A compelling argument for the idea that time may be a construction of consciousness comes from the philosophy of phenomenology, which studies how we, as conscious beings, experience things. According to phenomenologists such as Maurice Merleau-Ponty and Edmund Husserl, time is not something we experience passively, but rather something we actively construct. The past exists only as a memory, the future as an expectation, and the present as a moment of experience. In this view, time is closely linked to the structure of consciousness itself. Our brains create the past by storing memories, the future by generating expectations, and the present by integrating sensory input into a coherent flow of experience. So if time is something that consciousness constructs, could this mean that time is different for different living beings? Recent research into time perception in various species suggests this may be the case. For example, animals with faster metabolic processes, such as birds and insects, experience time faster than humans. Their brains process information at a much faster pace, meaning a few seconds could feel much longer to them. This explains why flies are so difficult to catch. They essentially live in a slowed-down version of time compared to us, allowing them to perceive and respond to threats more quickly. In contrast, larger animals with slower metabolic processes, such as elephants or whales, may experience time more slowly and perceive the world in long, leisurely bursts compared to our fast-paced lives. The connection between time and consciousness becomes even more interesting when we consider altered states of consciousness. For example, people who have psychedelic experiences often report profound changes in their perception of time. Time seems to slow down, speed up, or even disappear completely. These experiences suggest that our sense of time is flexible and can be altered by changes in brain state. Similarly, people in deep meditative states often report a feeling of timelessness, in which the boundaries between past, present, and future blur or disappear. This raises the possibility that time as we experience it is a construction of the mind that can be manipulated through changes in the state of consciousness. Another fascinating connection between time and consciousness comes from dreams. Time often behaves very differently in dreams than in waking life. Hours, days, or even years can pass in a dream, even though only minutes have passed in the real world. This suggests that our brains have the ability to compress or expand time in ways that are separate from objective time. Some neuroscientists believe that dreams provide a window into the way our brains construct the experience of time, showing how subjective and flexible it can be. However, the most profound connection between time and consciousness is seen in near-death experiences, NTEs. Many people who have experienced NDEs report a feeling that time is slowing down or stopping altogether. Some describe seeing their entire life flash before their eyes in a few seconds, while others speak of entering a realm where time no longer exists and is replaced by a feeling of eternity or timelessness. Although the exact nature of these experiences is not yet fully understood, they suggest that consciousness can reach a state in which time, as we understand it, is irrelevant. This leads to one of the most profound questions in philosophy and science. Could consciousness exist outside of time? Some theories in quantum mechanics and neuroscience suggest that time may be a property of the physical universe, and that consciousness, if it has a quantum or non-material component, is not bound by the same rules. In this view, consciousness might be able to exist in a state of pure awareness, outside of the flow of time as we experience it. The idea of timeless consciousness has been explored in spiritual traditions for thousands of years. Many Eastern philosophies, such as Buddhism and Hinduism, teach that the true nature of consciousness is eternal, and that our experience of time is an illusion created by the ego. In these traditions, enlightenment is often described as the realization of the eternal now, in which the boundaries between past, present, and future dissolve, and the individual becomes one with the timeless nature of the universe. Whether time is a construction of consciousness, a fundamental property of the universe, or something else entirely, remains one of the greatest mysteries of existence. Our experience of time shapes every aspect of our lives, from the way we perceive the world to the way we think about ourselves. But as we have seen, time may not be as real or as simple as it seems. In the end, The question of time and consciousness takes us to the core of what it means to be alive, conscious, and present in the universe. Whether time is an illusion, an emergent property, or a fundamental aspect of reality, our journey to understand it continues, as long as we are conscious beings experiencing the unfolding moments of existence. Time and immortality. Can we ever escape time? As we approach the final chapter of our exploration of time, we ask ourselves one of humanity's most compelling questions. Can we ever escape time? For as long as humans have been aware of the passage of time, we have dreamed of stopping it, slowing it down, or even living beyond its reach. Immortality has been a theme in mythology, religion, and literature for millennia, and now in the age of science and technology, it has become a real topic of research and speculation. But what would it mean to escape time? And is such a thing even possible? Our first approach to escaping time is biological. In many ways, aging is the body's clock ticking down, with each passing year bringing us closer to physical decline. But why do we age? Aging is a complex process caused by a combination of factors, including genetic damage, cell breakdown, and the gradual failure of the body's systems. One of the main factors of aging is the shortening of telomeres, the protective caps at the ends of our chromosomes. Every time a cell divides, its telomeres shorten, and when they become too short, the cell can no longer divide and eventually dies. This process is an important factor in aging and has led some researchers to focus on telomere lengthening as a possible route to longevity. In laboratories, scientists have already made progress in extending the lifespan of animals by manipulating telomeres, improving DNA repair, and optimizing cellular function. For example, researchers have been able to double the lifespan of mice through genetic manipulation, and experiments with CRISPR gene editing suggest that we may one day be able to slow or even reverse some aspects of aging. This is where biogerontology comes into play, the study of aging at the biological level. A famous example of an attempt at biological immortality is the immortal jellyfish, Turritopsis dohrnii, a species capable of reverting its cells to an earlier, juvenile state after reaching adulthood. This effectively resets her biological clock, theoretically allowing her to live indefinitely. While this process, known as transdifferentiation, is not something humans can replicate, it provides tantalizing evidence that under certain conditions, biological systems can escape the limitations of aging. Another possible path to biological immortality lies in the development of regenerative medicine. Advances in stem cell research and tissue engineering have already enabled the regeneration of damaged organs and tissues, and future breakthroughs could allow us to continually repair and replace aging body parts, effectively stopping the aging process. Some scientists believe that with the right technologies, humans could live for centuries or even millennia. However, even if we achieve biological immortality, we would still be living in time. Our bodies might no longer age, but time would continue to pass, and we would still be exposed to the risks and dangers of life in a physical universe. Accidents, illnesses, or cosmic catastrophes could end our lives no matter how long we live. So while biological immortality offers a way to escape the limitations of our current lifespan, it does not free us from the inexorable progression of time. The next frontier in the pursuit of immortality is digital immortality. The idea that we could one day upload our minds into computers and leave the biological body behind to exist as pure consciousness in the digital world. This concept, often referred to as mind uploading or full brain emulation, has been a staple of science fiction for decades. But recent advances in neuroscience and artificial intelligence suggest that it may one day be possible. The basic principle of mind uploading is that the brain, like a computer, is an information processing system. If we could map the precise structure and function of every neuron and synapse in the brain, we could theoretically recreate that structure in a digital environment, thus copying consciousness. The brain contains approximately 86 billion neurons, each connected to thousands of other neurons, forming a vast network that stores our memories, thoughts, and identity. New breakthroughs in brain mapping, such as the development of connectomics, which aims to create a complete wiring diagram of the brain, are bringing us closer to unraveling the brain's complexity. But uploading consciousness presents enormous challenges. The human brain is not just a collection of neurons. It is a dynamic, living system that is constantly changing in response to new experiences. Replicating this in a computer would require not only a static snapshot of the brain, but also a system capable of simulating the brain's constant activity. Furthermore, there are deep philosophical questions about whether a digital copy of a mind would actually be you or just a copy that behaves like you. If consciousness uploading becomes a reality, it could allow humans to overcome biological limitations. Uploaded consciousnesses could live in virtual worlds, free from the limitations of time and space. In a digital environment, time could be stretched, compressed, or even stopped. Imagine being able to experience centuries in a single second of real time, or pausing your consciousness for 1,000 years and then reawakening in the distant future. Digital immortality would allow us to exist beyond physical time, to escape time, in a sense. But even in the digital realm, there could be limits. What would happen to a consciousness that has existed for thousands or even millions of years? Could our minds handle an endless existence? Some philosophers and futurologists have speculated that boredom or existential weariness might set in, leading to a desire for an end, even in a state of immortality. The idea of living forever may seem tempting, but it raises profound questions about the nature of identity, meaning, and the human experience. One of the most radical ideas in the search for immortality comes from a strange corner of quantum mechanics: quantum immortality. This idea arises from the many worlds interpretation of quantum mechanics, which states that every possible outcome of a quantum event leads to the creation of a new universe. In this view, there are an infinite number of parallel universes, each representing a different version of reality. Quantum immortality postulates that if every possible outcome is realized in some universe, you will never die in any universe. Even if you were to experience a fatal accident in one universe, there would be another universe where the accident did not occur. As a result, from your subjective perspective, you might never experience death. You would always live on in a universe in which you survive. In this way, consciousness could jump between different universes and ensure that you are always alive in at least one of them. Although quantum immortality is an intriguing idea, it remains highly speculative and controversial. The many worlds interpretation is just one possible way to understand quantum mechanics, and even if it is correct, it is unclear whether consciousness could actually jump between different universes. Still, the concept challenges our understanding of death and suggests that time, at least in the context of individual experience, may be more flexible than we think. What is time? And is the singularity the end of human time? Finally, we must consider the possibility of a future technological singularity, a point at which artificial intelligence becomes so advanced that it surpasses human intelligence and leads to exponential growth in technological advancement. Many futurologists, like Ray Kurzweil, predict that the singularity could occur within the next few decades and would fundamentally change our relationship to time and mortality. If a superintelligent AI could solve the mysteries of physics and unlock new dimensions of time, it could allow us to overcome not only biological limitations, but also the nature of space and time itself. Some speculate that advanced civilizations may one day figure out how to manipulate time at the quantum level, create closed time-like curves, or even reverse the arrow of time. This could open up possibilities for time travel, immortality, or even the creation of new universes with different time laws. At the singularity, the distinction between biological and digital life could become blurred, and the boundaries of time as we know it could dissolve. Consciousness could exist in a state beyond time, where past, present, and future would be accessible simultaneously, or where time itself no longer has meaning. In such a future, the human experience of time, with its linear progression and limited lifespan, could become obsolete, replaced by a form of existence that we can barely imagine. At the end of our journey through time, we are left with more questions than answers. Can we ever truly escape time, or is it an inseparable part of our existence? Will we one day unlock the secrets of immortality, or is death a necessary counterpart to life? And if we do indeed transcend time, what will become of the human experience? Time, as we have seen, is both a scientific and philosophical puzzle that shapes every aspect of our lives and our understanding of the universe. From the ticking second hands to the expanse of the cosmos, from the smallest quantum particles to the infinite multiverse, time is the thread that connects everything. And yet time may not seem to be as fixed or fundamental as we think. Whether we one day escape time or simply learn to live better in the flow of time, one thing is certain: the mysteries of time will continue to challenge and inspire us for as long as time itself exists. The end of time. What happens when time runs out? In the larger cosmos, everything seems to follow a specific purpose. Stars are formed, galaxies rotate, life evolves, and civilizations grow. All these events are bound to time and unfold in a certain sequence, giving us the impression that the universe is driven by an eternal clock. But what if there comes a moment when this clock stops? What happens when time itself ends? This final chapter addresses the profound and disturbing possibility that time may one day come to an end. The ultimate fate of the universe is one of the most debated topics in cosmology. If time as we know it is linked to the physical universe, then the fate of time is inextricably linked to the fate of the cosmos. The Big Bang that created time and space may one day be followed by another event that marks the end of time. But what does that mean, and how could it happen? Let's examine the most popular theories about the future of the universe and their implications for time. One of the leading theories about the future of the universe is the Great Freeze, also known as heat death. This scenario is based on the observation that not only is the universe expanding, but that this expansion is accelerating due to a mysterious force known as dark energy. If this expansion continues indefinitely, the universe will eventually reach a state in which all matter is so widely distributed that no new stars can form, and all existing stars will burn out. As the universe continues to expand, it becomes colder and darker. Over trillions of years, all energy will be evenly distributed, and the universe will reach a state of maximum entropy. In this state, no more work can be done, no more complex structures can form, and there will no longer be any processes. Essentially, time would lose its meaning in a universe where nothing happens. Without events or movement, time would seem to stretch into infinity, but without anything happening, a cold, dark, and timeless void. In the Great Freeze scenario, time wouldn't actually stop, but it would become irrelevant. There would be no ticking clocks, no events marking the passage of time. In this sense, time would have run out, because it would no longer have any practical meaning. The universe would exist in a kind of frozen eternity, with no distinction between moments. An alternative scenario to the Great Freeze is the Great Contraction. This theory suggests that the universe may not expand forever, but may one day stop expanding under the influence of gravity and instead shrink. In this case, the expansion of space would reverse, and all the galaxies, stars, and matter in the universe would come closer to each other. Eventually, this contraction could lead to the collapse of the universe into a singularity, similar to the state it was in at the time of the Big Bang. The idea of the Great Contraction raises fascinating questions about the nature of time. If the universe contracts again into a singularity, could time itself reverse? Some theorists suggest that as the universe shrinks, the arrow of time, the forward path from the past to the future, could reverse, causing time to flow backwards. In this scenario, the future could become the past, and everything that ever happened could happen again, but backwards. Although this idea is speculative, it suggests that time may be nonlinear and irreversible. If time can reverse, It challenges our understanding of causality and forces us to reconsider what it means for time to end. Another more dramatic theory about the future of the universe is the Great Rift. This scenario arises from the observation that the expansion of the universe is accelerating due to dark energy. As the force driving this acceleration grows stronger over time, it could eventually reach a point where it overcomes all other forces, including gravity, electromagnetism, and even the forces that hold atoms together. In the Great Rift, galaxies, stars, planets, and even atoms would be torn apart by the accelerated expansion of space. Eventually, even space and time themselves could be torn apart. In this scenario, the fabric of space-time could collapse, which would literally mean the end of time. There would no longer be any space or time in which events could take place, and the concept of time itself would lose all meaning. The Great Rift portends a catastrophic end to the universe, with not only matter, but time itself torn apart by the relentless expansion of space. Time as we know it would cease to exist in this violent and final dissolution of the cosmos. While the previous scenario suggests the end of time, some cosmologists suggest that the universe could undergo a cyclical process, with each great contraction followed by a new Big Bang. This theory is known as the Great Leap. In this model, the universe contracts until it reaches a singularity, but instead of collapsing into nothingness, it bounces back, triggering a new phase of expansion. In the Great Leap scenario, time would continue through cycles of contraction and expansion. The end of one universe would mark the beginning of the next, creating an eternal rhythm of time. Time would not actually run out, but would reset itself with each new cycle. However, each jump could produce a universe with different physical laws, and time itself could function differently in each iteration. This cyclical view of the universe challenges the idea that time must have a definite beginning and end. Instead, it suggests that time could be infinite, extending infinitely into the past and into the future, through an endless series of cosmic rebirths. The fate of time is also deeply connected to our understanding of quantum mechanics and quantum gravity. While classical physics views time as a continuous and smooth dimension, quantum mechanics suggests that time, like space, could be quantized at the smallest scales. If this is true, time might not flow smoothly, but instead consist of discrete, indivisible quanta of time. Some theories, such as loop quantum gravity, propose that space and time are made up of tiny, discrete loops, much like the pixels on a digital screen. If time is quantized, gaps in time could exist at the smallest scales, and the concept of continuous time could collapse entirely. This raises the possibility that time itself could end at the quantum level, although it continues to appear fluid at larger scales. Quantum mechanics also brings into play the idea of superposition, where particles can exist in multiple states at the same time. This leads to the possibility that time could also exist in multiple states or timelines. In a quantum universe, time could be much more flexible and strange than we can imagine, and its end could not be a simple, linear event. What would the end of time mean for human existence? If time is closely linked to consciousness and experience, then the end of time could also mean the end of human consciousness. Without time, there would be no past, present, or future, no sequence of events, no change, and no experience. The end of time would mark the end of life, thought, and reality as we understand it. However, some speculative thinkers have pondered how humanity might survive or overcome the end of time. If we achieve digital immortality by uploading consciousness, it might be possible to preserve consciousness in a digital state, even if the physical universe expires. In a virtual reality, time could be simulated or manipulated so that conscious beings could continue to have experiences even in a universe where time has effectively ended. There is also the possibility that advanced civilizations will discover ways to manipulate time or even escape to other universes where time continues. In this speculative future, humanity could evolve into beings capable of existing beyond the boundaries of time and space and experiencing reality in ways we can barely imagine today. The end of time is one of the most profound and disturbing concepts in cosmology and philosophy. It forces us to question the limits of human existence and reality itself. Whether time ends in a cold, dark eternity, in a violent cosmic collapse, or in an endless cycle of rebirth, its fate remains one of the universe's greatest mysteries. Right now we live in time, bound to its flow and shaped by its rhythms. But as we continue to explore the universe and unravel its deepest mysteries, we may one day unlock the true nature of time and perhaps even find a way to overcome it.